Thank you for having me. I'm Alex, the entrepreneur, and this presentation is Fuzzing for Security Research for Beginners. I am a security researcher at Spearbit and Codarena. I was famously the best judge at Codarena, and before that, I was a developer at Badger. My smart contracts handled hundreds of millions of dollars in TVL, and as of today, I racked up about $500,000 in bounties, 200,000 from contests, and the rest from bounties. I co-founded Recon with Antonio Vigiano. We are a boutique audit shop that specializes in invariant testing, which I'm going to briefly talk about today. Some of our elite customers are Centrifuge, Badger, Korn, Liquidity, and Balancer DAO. And if you've been in any public or open source repo, you probably saw some of our work. We are amongst the most prolific invariant suite writers. We typically use Echidna and Medusa, and we developed a workflow that allows us to write Foundry tests and debug them with Foundry, which I'm going to talk about later. And we're kind of at the bleeding edge, I guess. I will take that guess, because we found bugs in most of these products, including Almos, Medusa, Echidna, and HEVM, simply because we really use this stuff every day for the past year and a half. I'm going to start from the basics. So what is fuzzing? Fuzzing is effectively throwing the kitchen sink at smart contracts to really see what happens. And so the key idea around fuzzing is that you're performing assertions over specific checks. So you want to think about specifying how your system works. And that brings a different paradigm of thinking, which is called declarative instead of an imperative mindset. And so the key idea is that you want to express how the system should work or how the smart contracts should behave, instead of explicitly stating what the smart contract should do. The key distinction between fuzzing is that you can have stateless and stateful fuzzing. They both are extremely important and useful. The stateless fuzzing consists of fuzzing, as in throwing random inputs at contracts without having any particular previous history. It's basically the idea that you will just grab your contract, you will deploy it, or you will set up a library, and then you will just throw some random inputs. This is how fuzzing was born, because it was born to fuzz, to test the CLI tools mostly, which tend to be stateless. And it's been adapted to be stateful for smart contracts, because smart contracts tend to have these hidden inputs in state. And so having the fuzzer explore some sort of a history in the sense of trying different combinations of states for a smart contract can then help you explore whether you can break some of these assertions. It's also worth mentioning that formal verification tools use a different idea, which is called weakest precondition, which is the idea that they will set the state of the smart contract system to some arbitrary state, and then they will see whether they're able to break the smart contract system off of that. So this makes formal verification very efficient, but it also makes it a lot less grounded in reality. Whereas stateful fuzzing always gives you a repro, meaning that when you break a property, you actually know how to break it, although it takes a lot longer to. And so how do you fuzz? At the highest level, you're going to have a tool called a fuzzer. Could be Foundry, Echidna, Almos, or Medusa. Then you're going to have your contracts, which are your either one contract or your smart contract system. And then you're going to have assertions, which are basically questions that you ask via the assert solidity function. One key aspect of fuzzing is that coverage is the most important prerequisite. Ultimately, the quality of your test is only as good as the amount of states that you can explore. And so coverage gives you a direct metric into how well you're doing at that level. And then there's a deeper idea around coverage, which is called logical coverage, which as of today, we don't have the tools to talk about. It's something that is extremely underexplored. And once you start using fuzzing professionally, logical coverage becomes an even more important idea. The last piece of information for fuzzing is that whatever setup you write will influence the results that you get, because you always have some sort of a bias around the setup of your contracts. And so that bias ends up influencing the results that you're going to get, as well as the possible state transitions that you're going to test. And I'm going to show this today, but you want to be mindful that early decisions will influence your results. And that's why fuzzing is, for many, or at least stateful fuzzing, is a very difficult technique to master, but tends to be a very easy technique to get started with, which I hope you'll try after this video. There are many other types of testing that you can do, so you should definitely go check this out as well. The simplest one is called parameterized testing. The Python people will say that's fuzzing. It's not exactly fuzzing. It's more of a way to templatize your tests. Formal verification is another amazing field of research. You should go check out Certora and Almos, as well as control. Then there's the branching tree technique, which is being pioneered by Paul Berg at Sablier Labs, which consists of enumerating all possible state transitions, and that allows you to then write tests in a more methodical way. And lastly, there's mutation testing, which consists of altering your source code in order to evaluate the quality of your tests. Mutation testing is also massively appreciated, and it can be really useful to determine whether your tests are good or not. So we're going to write our first fuzz test. We're going to use Foundry, and I'm actually going to show you a bug that I found in the Curvens smart contract system, which has kind of a bit of an history. Because this bug was originally in another code base called VMAX, and it was found by the people at Y Academy, which found a part of the bug, which I'm going to show, and they missed the other part, which I'm going to show later as well. But for the sake of our demonstration, we have a function called getPrice. We grab a Uniswap V2 pool, we get the total supply and the reserves, and then we compute the alpha DAO fair reserves formula, which basically takes the 2 times the square root of the 2 reserves, of the product of the 2 reserves, times the square root of the product of the 2 prices, and then it divides it over the total supply. And you can see on line 38 and 39 that I hard-coded the prices to be 118, meaning that in our example, we are fuzzing against a stable pair, meaning both tokens should have the same price. This is obviously a simplification, but this can help you illustrate how the formula works and also how the formula gets broken. So the first insight into fuzzing is that whenever you have a complex set of systems, such as a lending protocol, you can typically fuzz starting from a smaller component, in this case, just the oracle. And what I did for the sake of demonstration is I removed the vast majority of the dependencies so that the code is even easier to read, but also easier to test, because all time we spend setting up our test is wasted time. The only time that matters is when we actually break stuff. So at the most basic level, the way we will write the test would consist of first writing a contract, right? We just take the gist of what we need to test and put it into a contract. We then deploy that contract, and then we can finally perform some tests. And you'll see that we'll start with something really basic, and then we'll escalate from there. So this is a setup function that somewhat mimics how you will set up your testing environment. We will deploy a couple of tokens. Since we are using these stable pricing, meaning that both tokens have the same value, we deploy 2 tokens with the same decimals. We then deploy the oracle, and then have this setup fork function that deploys the bytecode of a UniV2 pool, and then we mint some tokens. Interestingly enough, we don't mint the maximum amount, which will be uint 256, but we mint uint 88. That's because from experience, there are not that many tokens that will go past the 2 to the 88. And it's not particularly useful to get a bunch of false positives from the 2 to the 256. So that's why I use uint 88. And the most basic test that you can write is really a unit test where you will do something and then you will check what happens. So in this case, I have this test basic mint, which is a Foundry test in which we take token A and transfer it to the pool. Then we do the same thing for token B. And then lastly, we call mint because that's how a UniV2 pool works. It grabs the current reserves, it compares them against the balance that is available, and then it gives you tokens based on that amount. And so this is not a fuzz test, this is just a unit test, but we can convert it to a fuzz test by simply adding a input. And this is why Foundry is an awesome developer tool. It makes it this easy to write a fuzz test. And what this means is that Foundry will run this test for a certain amount of times with a random value for the variable AMT. So you can customize the amount of times this is run. You can obviously provide different inputs, but fundamentally, that's what you're doing when you write a fuzz test with Foundry. And in our case, we are starting with the basics. We are providing a balanced amount, and we're checking for the price. It's interesting to note that the moment you write such a naive test of having uint256, you run into Foundry finding an edge case. In this case, the edge case is a revert. It's not a assertion failure, but the edge case that we have is that whenever you pass amount, which is a uint256, but as you remember from the deployment, we are limited to only 2 to the 88 tokens, then we can run into a underflow simply because we're trying to move too many tokens. And so this goes back to the idea that what your setup is influences the results that you get. Because I decided that I'm gonna only use up to 2 to the 88 tokens, then I'm now limited to the fact that my test cannot have a 2 to the 256 input. So we're gonna simply change our amount to the 88, and now we're actually gonna get a real edge case, right? This is a edge case that, as a developer, if I'm writing this test from first principle, I'm thinking about how the system should behave, then this test should surprise me. This reverse should surprise me because it means I didn't fully understand what I'm doing. In this case, this is a fairly common edge case that is tied to how Uniswap v2 protects against donation attacks, which basically UniV2 forces you to mint a certain amount of liquidity to the other zero, and then it transfers it. And so this DS-MAF sub underflow is basically that. It's the computed liquidity of our 419 token amount, which is results in an insufficient amount of starting liquidity, and it basically causes an underflow. And so there are many ways to solve it. I'm going to just use a naive minimum bound, which simply says that whenever we get to a value that is below 1E8, 100 million tokens, we'll basically, or 10 million tokens, we'll basically just add those. And so that's all we're doing. At this point, we have a fuzz test that is passing. We will then grab our price. If you think about our formula, which was effectively taking the two prices of 1E18 and then multiplying it by 2, then it's fairly rational to expect that the price is 2E18. And at this point, we know, our test works, our minting works, but now we should investigate how to manipulate the price, because Oracle manipulation is amongst the most common exploits, most common root cause for exploits. And so we really only prove that we're able to mint and get that price given a balanced amount. So the obvious next escalation will be to provide, we will simply add an assertion here, right? Assert EQ, get the Oracle price and verify that it's 218. But this should be fairly straightforward because we're providing the same amount of tokens. So this is just the next level of complexity. And a proper next escalation will be to try an imbalanced mint. We will provide an amount A and then an amount B. We will provide the naive minimum bound to both tokens. We will then transfer them, and then we will mint. And then we will assert that the price is constant, right? The Uniswap formula makes it so that whenever you perform a swap, the K in theory should only grow, but the fair reserve amount should be constant. And so our intuitive understanding of the naive formula, because this is a naive implementation, is consistent. And so what you'll find is that if you stop here, which is a very common level of complexity for most engineers and most developers, is to stop at a fuzz test. I fuzzed for all the amounts in the universe, arguably, or all the realistic ones. Maybe you will just change this to a check and you will run Halmos, and most likely you will miss what I'm about to show you because you stopped here. So this is a clear example of fuzzing in a stateless way. It's great. It gave us some edge cases. It made us think about the system, but we'll see very quickly that it's limited. So we feel like we're good. I can tell you we're not. And the people that go past this are the people that will find all of these bugs, whereas the people that stop here will simply be unable to, unless they are going to go through a more mathematical approach. So we're going to extend our test to be stateful, where stateful means that our tool will be able to do some random operation before, some random operation after, and then it's going to perform a test. Most people would have their first experience with this type of testing with Foundry. From my experience, having worked in this specific area of research for over a year and a half, Foundry is limited because of these three reasons. By default, it considers or reverts a failure, which is not useful to us because we want our fuzzer to just try a ton of random combinations, even if they're nonsensical. It doesn't have a coverage report by default. You have to actually request it separately, which is not particularly useful. And then the third thing is it's currently not coverage guided. There's work that is being done to make it coverage guided, but as of the past year and a half, it wasn't. However, Foundry is extremely fast and extremely good. So we use Foundry every day, but we use it to debug repros of bugs that are found by other tools. So in this presentation, I'm going to talk about Echidna. If you want to try other tools, you can also try Medusa. The interface between Echidna and Medusa is literally the same. And then in a few weeks or maybe months, Halmos is also releasing what they will call their invariant testing release. So everything that I'm showing you is only going to get better because the vast majority of tooling is supporting this. And as far as I know, Foundry is also supporting this very soon. It's just as of today, Echidna is a better tool, and so that's why I'm going to talk about that. So Echidna has a coverage-guided system, which means that the more, or rather, it prioritizes calls that will give you more coverage, and it stores them through a technique called corpus reuse, which makes it so that once you run Echidna once, it's going to be smarter for the next run. It has a dictionary that is integrated with Slither. It basically performs static analysis to figure out what to call. This can definitely be improved, but it's pretty good. It has a coverage report by default, and it has a few testing modes, which I'm going to show, because we're going to use different testing modes to go from what we will call a low severity bug to a critical exploit. So Echidna is written in Haskell, Medusa is written in Go. If you just want to use the tool, I will use Echidna. If you care about extending the tool, you will probably want to use Medusa, which is a more recent tool. You can find it at critic/Echidna, completely open source, GPL free. It's an awesome tool, and I believe it's the most underestimated tool in the Ethereum space. And I hope after this presentation, you will agree with me. So the installation is as simple as installing it with Brew, or you can also get a binary at GitHub. For the sake of explaining how Echidna works, I set up this demo contract. So this is what a classic Echidna test file looks like. You need to have a payable constructor because Echidna is really a beautiful mess. There's a lot of weirdness to it, but it's also a really powerful tool. So you just have to give it a payable constructor. It will revert for no reason. We then have a handler function, which basically helps us explore the state. In this case, it changes a variable inside of itself. But in a more complex scenario, it could change or interact with another Uniswap pool, which is what we're going to do in a few minutes. And then lastly, we have an assertion handler, meaning we have a function that asserts either true or false under some scenario. And it's basically how we're going to break properties. So in our case, our assertion failure would happen if the price is no longer the constant CHUI18. So to run Echidna, you will basically create a file in your Foundry project, and then you will type this command, echidna.-contract with the name of the contract and test mode assertion. And it will basically use Foundry to compile the project, and then it will run, giving you this cyberpunk type terminal, which whenever you break a property, in our case, the test consisted of calling out 1 3 times to break the check true property. This is what you will see. You will see a sequence of calls in the terminal, and then once you stop it, you will get some text that allows you to figure out how to repro this bug. Now, the problem with Echidna is that Echidna takes minutes to start. It's super clunky. You wouldn't necessarily be able to repro. And so what we created is called the Chimera framework. And it's basically a simple framework that makes it so that you can write your test in Foundry, and then you can use Echidna to break those same tests. And so for the suspension of disbelief, you can basically write Foundry test and use other tools that are more powerful to break those same tests. And so this is what the example project will look like. This is all the screenshots are taken from this project, both the Foundry test that I showed you before, as well as the Echidna code I'm going to show soon. But fundamentally, we have a setup file for the deployment. We have a target function file, which I'm going to show later, to move the state, to tell Echidna what to do in order to try new things. And then we're going to have properties which are used to check for specific assertions. So the setup should look very familiar because it's literally the same as the one for Foundry. And because of our framework, both tools will basically run with the same deployment. Then the target functions is basically taking the Uniswap pool and giving us a way to call that. You can see that there's a modifier called asActor. That's a convention we use where we are basically pranking the current actor so that all operations are done in a consistent way, and so that we can also abstract away having different actors. But for the sake of our demo, we could even remove that. At the end of the day, we're giving Echidna and Foundry a function that they can call to alter the state of the Uniswap pool. That's really all we're doing. And then we have this property that asserts, that handles an edge case, and then it simply asserts that the price is equal to CHUI18. So anytime you have an assertion that says that the price is CHUI18, you're basically asking the tool to flag anytime the price is not exactly that value. And we also have this edge case of the total supply being 0. When the total supply is 0, we just skip the check because we don't necessarily want to check it in that case. So in order to run Echidna, again, because it's an overly complex tool for, it was a cutting edge tool in 2021. So you need to run this dorky command of Echidna --contract tester, etc. But we typically just copy paste it. We also have an extension to run this type of stuff. And after a few seconds, Echidna will actually break this test very quickly. And so because we escalated from using Foundry in a way that is hard-coded into something that is no longer hard-coded, because we asked the tool to try a bunch of combinations in just checking the property, we're actually now able to break it. So our job after we break a property is to figure out if this is due to a known root cause, meaning this is most likely a QA or some informational bug, or whether this is something that we should investigate further because it's serious. So after you run Echidna, Echidna goes into what is called shrinking mode. It basically shrinks down a sequence of calls to a simpler version. And so you can see that what Echidna did is it donated one way to the pool, it called sync, it then donated again, it switched to the asset 0, it donated the asset 0, and then it called mint. And so roughly speaking, what it did is it donated to the pool and then synced it in an imbalanced way. It then donated a token, switched to the other token and donated that one, and then called mint. So it basically did a proper mint, but before doing a proper mint, it also donated to the pool and called sync, and it broke our property. So once we see something like this, we know that something is up. However, it can be very difficult to use Echidna to debug this, because that's all Echidna does. It tells you, this is what I called, is a log, good luck. And so what we will do, what we built is we have a scraper that can convert your Echidna test into Foundry repros. And so that's what we will do. That's why we created an entire framework around this, because we want to use Echidna, which gives us so much more, so many more combinations, so much more power. But Echidna is extremely clunky, so we just grab what Echidna gives us, convert it to Foundry, and now we can debug with Foundry. We also have an extension. It's free on Visual Studio Code. Just make sure to download it from recon-fuzz. Don't get fished. And basically, that would wrap running Echidna, and then it will also scrape it into giving you a repro. And so once you run Echidna for the extension, it would ask you whether you wanted to generate a repro, and it would give you something like this, which, as you can see, matches the previous description of donating some token, calling sync, then performing a real mint, and then checking the property. And now we have a Foundry repro of the price being wrong. So once you get to this point, this is where the magic is going to happen. So because at this point, we have a low severity bug, right? We have a low severity bug that says that we can move the price by about maybe 10 basis points or 1 basis point. It's like a very small amount of an impact. However, you, as a proper security researcher, you wouldn't stop here, because now you have some sort of a precondition. We know we need to donate. We know we will then mint, and the price is going to break in some way. So what you will do as an extremely common approach, which, as far as I know, you're forced to do this with Foundry, Almos, Control, and Certora. Like every tool except Echidna Medusa forces you to use a tolerance. So what we will do is we will rewrite our property to say that we're going to grab the price, and then we're going to require not that it's exactly 318, because obviously we broke this one, but we're going to just add some sort of a tolerance of, let's say, 10 basis points, 1%. We're like, as long as the price is within 1%, it's okay. We're going to change the LTV. That's a very common way of thinking for most developers, especially because, if you spent 9 months on a project, you don't exactly want to go back to the drawing board when we break your Oracle. And so from my professional experience, once you get to this, you will not have the buy-in of the team to change their code, because this is a low severity bug. And most people will stop here, but we're not going to stop here. We're going to go past this. So once we will break the property with a few tolerances, let's say we get to 1%, 2%, 5%, this is where this type of testing is just unacceptable. It's just not going to get us anywhere. And in theory, most tools that have symbolic execution should be able to optimize a value, but in practice, none of them offers this technique. So we're going to use the good old clunky Echidna in optimization mode by setting these echidna.yaml config file. We change the test mode to optimization. We put a prefix called optimize, and then we write these two functions, optimize underscore price underscore below, which returns a int 256. These are all convention of, again, this clunky tool that I'm going to show you is extremely powerful, but it's very clunky. And it returns this signed integer. And the way optimization mode works is it actually only returns the maximum value. So we separate the deviation of the price in a below, meaning we are testing for values that go below the 2E18 price, below the floor, basically, and prices that go above. And so we kind of write these properties in this way, where we grab the price, and then in the first version, if the price is below 2E18, we return 2E18 minus the price, because the lower the price, the higher the return value will be, meaning that 2E18 indicates that our price is 0, which would indicate that we basically broke. We can literally self-liquidate at any time. And then the opposite property will assert that, or rather will check for the maximum value whenever price is above 318, meaning any value that is very high will lead us to a critical exploit that will typically allow us to overborrow by orders of magnitude, possibly. And that's what you would actually then have the tool do. It will run with only 2 tests, and it will give you these 2 values. And you can see very quickly that I don't need to know exactly what's going on, but what Echidna is telling me by just looking at it is that there's this insanely big value for a property. And if you check up here, it's optimized price above is massively big. And so this is part of our workflow at Recon. Once we have a precondition, we run the optimization run, which basically gives us a higher theoretical maximum. It's not actually the real theoretical maximum because the fuzzer is just trying random values. And so it technically is not the maximum impact. However, in practice, Echidna tends to be pragmatically giving you a very high value. And so once you have such a value, you typically are able to escalate it yourself. So we know there's a big value in the price above, right? Meaning that our delta of the price is abnormally high. This will go from a low severity, let's just dismiss it, we're done, to a, okay, you have to stop everything. Either this bug is fully discovered or we cannot ship this type of project. It's just, that's the level of severity we're in. We don't have the root cause yet, but this will be a precondition for a war room. So this is the type of scenario that we were able to construct by simply using a tool that is good for this type of job. So at this point, there's another clunkiness about Echidna. If you just run it and you don't let it end, it's not going to shrink, meaning that our repro will be about 100 lines of random stuff to get to this value. So it's absolutely unusable. However, you can run Echidna with the same corpus because Echidna remembers what it tried. You will simply rerun it with a low test limit to trigger the shrinking mode. And so you're going to run into another bug because the other property we wrote, optimize price below, is basically we return the maximum value at all times because as a matter of fact, the formula we are using provides a floor that makes it so that you will never have a value that is below 318. So that's consistent. But because of that, we actually have to comment out this test. Otherwise, Echidna will break. And now we can finally get a repro that is shrunk and that is simple to understand. And it will look something like this. We had our oracle that we thought was going to break by 10 basis points or by a joke, right? We had a low severity bug nobody was going to look at a second time, actually escalated up to a critical exploit where the price was manipulated by an order of 10 to the 36. It's literally an insane exploit. We basically we broke the system past any reasonable level of skepticism, and all we did is very similar to the previous version. We donated to the pool, we donated a second token, we mint, and then we basically donate a few more times in an imbalanced way. And the reason why this actually happens is that the formula that I showed you at the beginning of the call doesn't account for post-arbitrage reserves. It takes the reserves at face value. And so anytime you take the reserves at face value, you will have a floor, but your maximum price is actually unboundedly exploitable. And so this is literally the story of how I went from a low severity bug to a critical bug. And the reason why I found it was that by pure coincidence, instead of fuzzing the router, because the router always performs a swap in a non-arbitrageable way, I started fuzzing the pool just out of curiosity, and that's how I actually ended up finding this bug. And obviously, once you find this type of bug, you will then try to fix it, and you will then want to reuse the corpus so that this type of test never breaks again. This is why we built Recon. You can see an example on the Liquidity V2 governance repo. It's public of them. Anytime they push a new code change, this will automatically run and hopefully give them better assurances than simply running a stateless fuzz test for a few minutes. So hopefully I inspired you to go fuzz. You want to simplify the system. You want to do a stateless fuzz. You want to then add more inputs. And then you want to go and escalate to using a stateful fuzzer. And once you start breaking stuff, you go into optimization mode and you optimize until you are confident that the system is safe, or you're actually able to leverage that into a more severe exploit. If you're interested in joining us in the journey, we have a Discord community at getrecon.xyz/Discord. And there's also a few resources you can find in the Discord, but you can also go check them out. We have our book.getrecon.xyz, which helps you write invariant tests with some of our tooling, such as our extension and our other online tools. We also have a Substack where we post our periodic updates and retrospective from our customers, as well as some events. And lastly, you can follow us on Twitter, x.com/getreconxyz. I'm Alex the Entrepreneur, and thank you for watching. Have an awesome one.